So recording. Okay, so the topic is air and water. It's a very small topic, and I like to call these flyby topics. And when I say flyby, we literally, it's in today, out tomorrow kind of stuff. It's not like a topic we have to go into great detail about. And it's just a lot of learning work that you have to just read the notes a couple of times, make a few extra summaries, and then just basically remember what was in the notes. Cool. Test for water. Do you remember we did testing for anions and cations and all those things? You guys vaguely remember that testing for sulfates, nitrates, chlorides? Yep. So it's the same kind of concept, except this time we're literally testing for the presence of water. So use your imagination a little bit. I give you a clear liquid, and it could be anything. It could be pure ethanol. It could be pure petrol. It could be pure benzene, whatever. But it's a clear liquid, and you want to know, does this liquid contain water? So you need to develop a test that is going to test for the presence of water. And one of the tests that we can use is what's called anhydrous or white copper sulfate. And if water is present in the liquid, the copper sulfate will turn blue. Has anybody seen this? Has Mrs. McCarthy showed you, or did you see this anywhere else?
Yes, I did it with her, I think. Yes.
I think she often does this. I think this is a reaction that she's quite familiar with. So I think she does do this. So I'll show you later what we do. We first make the white copper sulfate by heating the blue one, and then we add the water back. So it's quite cool because it's literally a white powder, like you can think of chalk or something, and you add the water and it turns blue. So you can see the image at the bottom here. There's a little bit of white at the bottom. That's the unreacted one. And you can see the blue that's formed at the top. That's the one that's had the liquid dropped on top of it. Cool. And then another one you get is the cobalt chloride strips. And these literally come like in testing paper. So when you think of litmus paper, you get the red litmus and you get the blue litmus. This is also a type of paper that we called cobalt chloride paper. And it starts off as blue. And if you dip it in a solution that contains water, it turns pink. Cool. Has anyone seen this? Maybe Laura, you saw this one?
I haven't seen this, so.
Okay, so I've got this in the classroom. I'll make a short video of it and upload it. So I'll make a video of myself doing this and then I'll upload it for you to watch. It's quite a nice reaction because you can actually reverse it by evaporating it, and you leave it in the sun to dry and it turns back to the blue again because you remove the water. So it's a reversible process, which the extended students will see a bit later. Also, the summary of the tests. If you heat the sample in a test tube and if the gas released is liquid water vapor, then the blue cobalt chloride litmus paper or paper will turn pink. And if you have a liquid that you add the drops to, you can add the drops to the anhydrous copper sulfate and that turns blue. So literally the only thing you actually really need to know is the summary of the table. So this table here that's on the bottom of the page, that's the important thing. Cool, any questions?
No, sir.
No? Okay, so I'll give you a scenario just to make you think a little bit. If I took the anhydrous copper sulfate, which is white, and I added pure ethanol to it, would it turn blue? Anybody? So I'll repeat the question. The question is, if I took anhydrous or white copper sulfate and I added pure ethanol, so just ethanol, nothing else, would the white copper sulfate turn blue? Anybody? No? Okay, so the answer is no. And the reason is because if it's pure ethanol, it doesn't contain water. So the only thing that's going to turn it from white to blue is water. Cool. Treatment of water. You don't need to study this diagram in detail. This is just something I found off the internet so that you can see a schematic. But when you think about if you were going for a walk somewhere where there was a river, don't read the notes. Just think to yourself, what would you do to the water before you drank it?
Filter it.
Filter it, yeah. So it makes sense that there might be a little bit of sand or debris or plant matter or whatever, like there's something in the water. So you could use like a sock, or you could use a scarf, or you could use a t-shirt, or if you have a coffee filter, just happen to have one in your backpack, you can use a coffee filter or whatever. But yeah, you would filter the water, and it's obviously to remove the large contaminants. But does that mean it's removed everything that's potentially dangerous?
No.
No, because there's other things that are microscopic that could also be dangerous, and that'll go through the filter. So for example, it might contain bacteria or parasites or something like that. So this is not in the notes. This is a thinking question. What would you do to the water if you had the ability to do it while you were hiking or camping?
You would boil it.
You would boil it, correct. You would heat it. So you would heat it to a very, very high temperature to hopefully kill off all the pathogens. So if we were going to do that with our entire water supply, you can imagine how much water we use. I mean, think about how much you use at home every day. Would it make sense for them to boil every single drop of water that they collect and send to your taps?
No.
No, because it would use ridiculous amounts of money. You can imagine like a swimming pool. Imagine a large swimming pool, and imagine trying to heat that swimming pool to boiling point. It would take forever, and it would use stupid amounts of energy. In fact, I don't think you'd ever get it to heat up to boiling point because you would never have enough energy to do it. So what do they do instead of adding? What do they do instead of heating it?
Add chemicals.
Add chemicals, correct. And the main thing is chlorine. So they often chlorinate the water. So very often when we have outbreaks of diseases and stuff, or cholera or E. coli, you can often smell your tap water smells a little bit more like pool water, if that makes sense. Because they put a bit of extra chlorine. But the chlorine is not harmful, because what it does is it reacts with the water and it forms chemicals which you would otherwise find in the water itself. So in low doses, the chlorine itself is not poisonous. Obviously, you wouldn't drink pool water because that's highly concentrated, but in small doses, you can drink it. Has anyone ever used chlorine tablets when they've traveled?
Nope.
So you can actually buy it at a pharmacy. You can buy chlorine tablets. And if you're traveling to, let's say camping, that's a good example. If you're camping and you're drinking the water, you could use the chlorine tablets. Or if you're traveling to, let's say, Windhoek, where you don't trust the tap water, you could add the extra chlorine tablets. So you can actually buy them at a pharmacy. Or you could use the pool chlorine, and you could use it in very, 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 very small doses. So you could work out a small concentration that would be safe to drink. Cool. So the summary that you need to know is that the water is first filtered to get rid of the large contaminants. And then the second thing you need to know is that we add chlorine to kill off all the microscopic organisms. Cool. Any questions? Nope. Cool. So this is what happens at the water treatment plant. Walvis Bay does it quite well. Our municipal water is actually super safe to drink. There's very little wrong with our water. Okay, so this is for the extended only, but the core guys, you can kind of just have a listen in any case. When I talked about the copper sulfate and I talked about heating it to produce the white one, what I meant was that I can take the blue copper sulfate and I can heat it to make the white copper sulfate. So the crystal starts as blue, and what I do is I put them on a Bunsen burner, I heat it, and the water that's inside the crystal evaporates and it turns white. So I'll do this again. I'll either link a video or I'll do it myself and send you the video. But it's quite cool because you literally heat it and it turns from blue to white. And the reason is because you're removing the water. Cool. And then the reason why it's reversible is because when you add the water back, the white turns back to blue. Cool. Any questions there?
No.
No, anyone? Okay. And in terms of endothermic, exothermic, you don't need to know endothermic, exothermic, but it's good to know that endothermic means you added heat and exothermic means that you gave off heat. And it makes sense that trying to remove the water is endothermic because you have to heat it to evaporate the water. So you have to supply the heat for that to happen. Also, the forward reaction would be endothermic and the reverse reaction, therefore, would be exothermic. Cool. Any questions there?
No, sir.
No, we good. And then the last page is for cobalt chloride, exactly the same thing. you can take the pink cobalt chloride, which has the water, you can heat it, and you can form the blue cobalt chloride, which doesn't have the water. And then you can reverse the process by taking the blue cobalt chloride, adding the water, and forming the pink cobalt chloride. So we can literally go back and forth between pink and blue by adding or removing the water. Cool. Any questions?
No, sir.
No.
So would you agree with me that it's what we could consider a flyby topic? There's not a lot that we have to know, and there's not a lot we have to understand. It's just a few things to remember.
Sure.
Cool. Okay, so what we'll do is we'll take a 5-minute break. I'll upload the next slide or the next topic, and then let's be back at 20 past. Cool?
Yes, sir.
Good. So please don't take too long. I'll give you till about 21, 22, then we'll start the next lesson. So don't go too far. Cool.